The control room is almost dark. Only one monitor is awake, washing the walls in pale blue light. On it, a simulated universe blooms into stars and filaments. A ghostly copy of the cosmos. A scientist takes the mouse, slides one tiny parameter a little lower, and watches everything collapse into a featureless fog. She pushes another parameter slightly higher, and this time nothing forms at all. No galaxies, no stars, no structures. Just a sterile sea of radiation that never cools into anything interesting. Here is the unsettling part. The real universe, the one outside that control room, appears to sit in a very narrow region of possibility. Change the basic numbers that describe its particles and forces by what seems like a modest amount, and you do not get a slightly different night sky. You get no night sky at all. Yet if there truly is a vast space of possible universes, and if life can emerge in many of them, why do our measurements keep placing us so close to what looks like a cliff edge, where a small shift would erase everything that makes us possible? Are we meant to read this precarious position as a sign of purpose, as if someone tuned the dials with careful intent? Or is it a statistical mirage that always appears when small creatures try to understand an unimaginably large landscape? And if it is only a mirage, how would we ever know? When we are trapped inside just one point on that landscape and can never step outside to compare. If this kind of perspective resonates, please like and subscribe to the Quiet Universe channel. Imagine that the space of all possible universes is an ocean, cold and black, stretching in every direction. Along one edge of that ocean lies a thin strip of sand where the water is just shallow enough to stand, and the land behind is not yet a sheer wall of rock. On that strip, waves can break, rivers can meet the sea, and fragile villages can cling to the shoreline. Everywhere else, the water is either crushingly deep or so thin that there is no shore at all. Now imagine that you only ever knew that strip of sand. You would walk along it, look left and right, and see only a narrow world. You might not even suspect that on one side lies a lethal abyss, and on the other a barren interior where nothing similar to you could exist. You would simply assume that the conditions you see, mild enough to allow your survival but never entirely safe, are the normal state of things. That is where our own universe appears to place us. When physicists treat the fundamental constants as coordinates on an abstract map and use their best theories to mark where long-lived stars and complex chemistry can exist, most of the map stays blank. Only a narrow band, that thin strip of sand, is colored as habitable. According to our instruments, the values we actually measure lie close to one edge of that band, close enough that small shifts would take us back into the blank. In plain terms, it looks as if the universe we inhabit is barely good enough for life, not lavishly friendly to it. It is tempting to turn this into a story of intention. If the habitable region is tiny, and we are inside it, perhaps someone or something chose those values with a goal in mind. The plot almost writes itself. The universe is special. The numbers are just right. And our existence is the payoff. Yet that story, however emotionally satisfying, leaves a scientific itch unscratched. Before we reach for intention, we ought to ask a simpler question that hurts more. Could a universe that feels delicately balanced from the inside be exactly what you would expect from blind statistics alone? This is not a question about philosophy in a vacuum. It is driven by measurements. Particle colliders track how unstable particles decay, revealing their masses and lifetimes. Telescopes watch how light curves around invisible matter, telling us how much mass is hiding in the dark. Precision clocks, frozen in quiet laboratory rooms, respond to tiny changes in gravity and motion. Together, they whisper the same thing. The constants of nature are not wildly flexible. Shift them too far, and the structures we rely on for our very existence do not form. Yet the way we visualize that fact is dangerous. We sketch a diagram with a shaded region labeled habitable and draw a dot near its boundary for our own universe. The human mind is wired to read that picture in a very particular way. We ask why the dot is near the edge rather than near the center, as if center means safe and edge means special, but in very high-dimensional spaces, the ones with many independent numbers. Edges and centers behave nothing like the familiar versions we see on paper. This is the deeper paradox. The more we learn about the delicate dependence of our universe on its fundamental numbers, the more reasonable it seems to say that we live near a boundary. At the same time, the more we learn about the geometry of high-dimensional spaces, the more suspicious we must become of words like near and typical. Does our uneasy feeling about being on a knife edge reveal something profound about the way universes with observers are distributed? Or does it reveal that our intuition about maps and distances simply breaks down when there are too many directions to consider? You are meant to feel slightly off balance here. When the numbers suggest that our cosmos is barely habitable, they brush against the human desire for safety and inevitability. We would like to believe that if the universe had been a little different, life would still have found a way. Instead, the calculations hint at a harsher truth. Most universes, if they exist at all in that abstract space, would never know stars that live long enough to warm planets or seed chemistry with heavy elements. In that light, our presence feels less like a guarantee and more like a fluke. At the same time, there is another way to look at the same scene. If nearly all combinations of the fundamental numbers lead to sterile emptiness, then perhaps it is no surprise that any observers who appear will find themselves in one of the rare universes that sit right up against the limit of what is possible. The shoreline may be thin, yet if all villages stand on shorelines because they need access to both land and sea, then of course most people will report that they live near the edge. So, which is it? Are we living proof that the cosmos is tuned with exquisite care, or are we simply the kind of beings who can only exist in places that feel precarious from within? To move even a little closer to an answer, we have to step away from the comforting drawing of a shaded region and a single dot, and learn how to read the entire map on which that picture sits. Picture a coastline viewed from far above. The sea is not made of water, but of possible universes, each wave representing a set of physical numbers that could, in principle, define reality. Across that ocean, almost every combination of constants drowns in sterility. Only a narrow band of sand at the edge allows the long, fragile interplay of forces that gives rise to stars, atoms, and chemistry. Our world stands somewhere on that band, not in its center but close to where the water laps against the dry land. For centuries, humanity imagined the cosmos as immense, yet simple. It followed precise rules, and those rules seem stable. The discovery that those rules depend on delicate numerical values changed everything. The masses of protons and neutrons differ by less than 1%, yet that sliver decides whether stars can synthesize elements heavier than hydrogen. The strength of the nuclear force determines how nuclei bind. The strength of electromagnetism shapes how atoms bond, and gravity's feeble pull decides whether the universe expands into emptiness or collapses before stars ignite. Each parameter lies within an astonishingly narrow window. Adjust any of them, and entire categories of structure disappear. Why are they just so? Why does the universe seem tuned so precisely to stand on this shoreline instead of sinking into the depths or rising onto barren cliffs? The question is not whether life can arise, but how the environment for life seems perched on the edge of impossibility. It would be natural to assume that among a vast sea of possibilities, most observers would appear in universes far from any boundary, where conditions are robust. But the more carefully we measure, the more precarious our place appears. In laboratories, physicists simulate slight alterations of those constants. A heavier electron changes chemistry beyond recognition. A weaker, strong force leaves nuclei unstable. Even the faintest alteration in gravity's strength reshapes the age and brightness of stars. If the universe were a dial board, every knob would sit within a hair's width of failure. Yet here we are, breathing on the beach, with the sea of sterile worlds on one side and the cliffs of instability on the other. At its core, this shoreline picture is both simple and deceptive. Simple, because it gives an immediate image of where we stand. Deceptive, because it tempts us to imagine a map that might not exist in any literal sense. The constants are not coordinates we can travel among. They are embedded in the fabric of our cosmos. Still, the metaphor captures something essential. There are many more ways for a universe to be dead than to be alive. Suppose we tried to chart that sea in a computer model. Each axis represents one constant, each point a different universe. Even with 10 or 12 constants, the dimensionality defies visualization. Yet mathematical sampling shows a pattern. The volume of viable space, the region that yields long-lived stars and stable matter, is minuscule compared to the entire range of parameters we can imagine. It is as if all of existence balances on a narrow ridge. One might think that being close to the edge is merely coincidence, or an artifact of our limited perspective. But the numbers do not cooperate with that optimism. Take the neutron to proton mass difference again. Make neutrons only slightly lighter and they never decay, flooding the early universe with heavy elements that prevent normal stars from forming. Make them slightly heavier and hydrogen dominates, robbing the cosmos of carbon, oxygen, and iron. The usable chemical diversity collapses. The line between survival and emptiness is razor thin. Why would any random draw from the cosmic lottery land on that narrow ridge? The question invites two kinds of answers. One is the design hypothesis, that some mechanisms set the parameters intentionally. The other is the statistical view, that there are countless universes with different constants, and observers can only appear in those rare regions where conditions permit. Yet both interpretations face a deeper puzzle. If observers can exist anywhere within the habitable band, why do we find ourselves near its boundary instead of deep within its interior? To see why that matters, imagine villages built along a coastline. If the beach were wide, with fertile land stretching far inland, most settlements would lie comfortably away from the surf. Only a few would risk standing at the edge. But if the coastline is extremely narrow, then nearly every village will seem to live dangerously close to the tide. The villagers might misread that pattern as special or intentional when it is simply geometry. In everyday language, our discomfort with living near the edge might not indicate divine precision, but a natural statistical bias. If habitable regions are thin, most observers must live near boundaries because there is no spacious center to occupy. Still, that reasoning depends on assumptions we have not verified. We do not yet know how the constants are distributed in the underlying landscape of physical laws. We cannot test whether universes with different parameters actually exist. All we have are our measurements, our equations, and the eerie sense that the cosmos we know occupies a knife-thin slice of possibility. This sense of fragility can feel personal. When we look at the night sky and realize how easily those stars could fail to exist, the universe becomes not only vast, but strangely temporary. The realization invites humility. We are not living in a system designed for our comfort. We are balanced, perhaps by chance, on a margin between silence and chaos. Why it matters is not limited to philosophy. The recognition that our constants occupy such a narrow range drives the search for deeper laws. If those numbers are consequences of hidden symmetries, then the shoreline might not be arbitrary at all. Perhaps there is a deeper ocean current that shapes where islands can form. Understanding that current could transform fine-tuning from mystery into inevitability. Until then, the shoreline remains our best metaphor for the conditions of existence. We stand where stability meets collapse, where the waves of impossible universes break and retreat. Our instruments, from colliders to telescopes, measure the ripples of that surf, trying to reveal why the sand beneath us does not sink. But if this boundary is truly so thin, we must ask another question before moving on. Could it be that our view of narrowness is itself distorted by the strange geometry of possibilities we cannot yet see? On a quiet table sits a single orange. Its skin glows under the light, rough but symmetrical. A simple object with a hidden lesson. If you slice it, the peel is thin, the flesh thick. Most of its mass lies safely within, but increase the orange's dimensions in your mind, from 3 to 5 to 10. Keep its density constant, and something strange happens. The peel begins to claim more and more of the total volume. By the time you reach hundreds of dimensions, almost everything that once felt like interior has migrated outward. The orange has become a hollow ghost of itself. This is the essence of a mathematical truth known as the concentration of measure. In spaces with many dimensions, the bulk of any volume collects near the boundary. What we call the inside shrinks to almost nothing. It means that for systems defined by many variables, being near the edge is not rare but expected. Our intuition, trained by a three-dimensional world, cannot see it. We imagine thick cores and small surfaces because that is what our eyes and hands have known. But the geometry of high dimensions betrays those instincts. When physicists talk about the space of possible universes, they mean a space where each axis corresponds to a fundamental constant, one for the mass of the electron, another for the strength of gravity, another for the density of dark energy, and so on. Even if we choose only 10 or 15 such constants, the resulting space is immense. According to the mathematics of concentration, almost every point in that space lies close to some boundary. If the conditions for life occupy any contiguous region, then observers like us should nearly always find themselves near its outer edge. So perhaps the shoreline that seems suspicious in the previous chapter is not suspicious at all. It may be a natural outcome of geometry itself. The fact that we appear close to a limit could be a generic property of high-dimensional possibility, not a cosmic clue. Yet this conclusion, tempting as it sounds, leads directly into a new trap. To speak of what is typical, we must know how to measure closeness, area, or probability in that abstract space, and that is precisely what we do not know. In plain terms, whenever we say something is common or rare, we are secretly defining a measure, a way of counting the possible cases. Change that measure, and your definition of normal changes with it. Imagine you are standing on the skin of that hyperdimensional orange. You have two ways to define distance. One measures the straight line between points through the interior. The other follows the curve of the surface. In low dimensions, these are nearly the same. In high dimensions, they diverge completely. A small patch can represent a huge portion of the total area, depending on which definition you choose. What feels like the center in one metric can become the boundary in another. This ambiguity infects our attempts to reason about universes. When we say the constants are fine-tuned, we are really saying that the range of values compatible with life is small compared to the full range we imagine possible. But how wide is that full range? Infinity on one axis and infinity on another yield no ratio at all. Unless we specify a measure, our sense of rarity is undefined. Mathematicians know this pitfall well. Without a proper measure, you can make almost any region look large or small simply by rescaling coordinates. The same trick of perspective that makes the orange's peel dominate its volume can make one set of universes seem vanishingly unlikely, while another appears inevitable. The measure trap is the quiet hazard behind every claim of fine-tuning. Why does it matter? Because this trap decides whether our apparent precariousness is evidence of design, evidence of geometry, or simply a mirage. If you pick a measure that treats every possible value of each constant as equally likely, you find the life-permitting region absurdly tiny. If you pick a measure that weights the constants according to some physical law, that same region can suddenly swell. The conclusion flips not because the data changed, but because the ruler did. The dilemma is not purely academic. In cosmology, when researchers model the early universe, they must decide how to define probabilities over an infinite set of initial conditions. Two groups using the same equations but different measures can reach opposite predictions about what kinds of universes are typical. One finds that life is almost impossible. The other finds that life is expected. The difference lies in the invisible act of choosing how to count. Think of walking through a forest in dense fog. Each step reveals only a small circle of visibility. You might think the clearing you find is rare, because you have seen only fog for hours. But perhaps clearings are scattered everywhere, and your narrow path has misled you. The measure problem is our cosmic fog. We see one clearing, our own universe, and we infer its rarity without knowing how the rest of the landscape is distributed. Some physicists try to dodge the trap by appealing to the idea of a multiverse, a vast ensemble of regions where the constants take different values. If such a multiverse exists, we could, in principle, define our measure by counting how many regions contain observers like us. But this only pushes the question back a step. What counts as one region? How large should it be? When the number of regions is infinite, any ratio of two infinities becomes meaningless without careful regulation. To put it another way, we are trying to weigh universes on a scale that has not yet been built. Still, the geometry offers an intriguing clue. If high-dimensional spaces naturally favor boundaries, then perhaps we should not be surprised to find ourselves near one. It would be stranger if we were not. The hyper-orange teaches that what feels like a rare position can be mathematically inevitable. What needs explanation is not that we live near the edge, but that we ever expected to be far from it. This realization flips our sense of the fine-tuning paradox. The apparent precision of our universe might not require deliberate calibration. It could emerge automatically from the shape of possibility itself, like drops of rain that always collect on leaves rather than in midair. Observers may always find themselves where the geometry makes their existence more probable. Yet the trap remains. To say that something is more probable presumes a way to count. If we cannot define that counting, then any statement about typicality floats without anchor. We can speak of oranges, hyperspheres, or infinite landscapes, but until we solve the measure problem, our arguments hover between poetry and mathematics. Why it matters is simple. Without a stable measure, cosmology risks mistaking its metaphors for results. When we call the universe fine-tuned, we may only be confessing ignorance about the correct way to measure possibility. When we call it typical, we may be doing the same. The boundary between precision and illusion blurs. Somewhere in this ambiguity lies a path forward. If geometry can explain why we live near an edge, perhaps projection can explain why we think we see a center. For that, we must look not at the orange itself, but at its shadow. In a darkened hall, a beam of light shines through a narrow slit onto a suspended model of a cube. On the wall behind it, the cube's shadow stretches and twists as the light moves. When the beam strikes directly, the shadow looks perfect. Tilt it even slightly, and the shadow distorts, shrinking one side and stretching another until the cube appears to fold in on itself. What if the same principle applies to the universe we see? That our center and balance are just the projection of something that exists in higher dimensions. Our minds are bound to three-dimensional intuition. We talk about up and down, center and edge, inside and outside, but physics deals with equations that live in spaces far beyond that. To describe all the constants and initial conditions of a universe, one might need 10, 20, or more axes. We cannot picture those axes. Yet they determine what kind of universe unfolds. A small displacement along one of them could change everything from the mass of a star to the stability of a proton. If our view of those axes is limited to a lower dimensional slice, we might mistake a skewed projection for a true pattern. Think of a sphere lit by a flashlight. Its shadow on the wall is a circle. Rotate the sphere and the shadow barely changes, yet shift the light and the circle stretches into an ellipse. Observers living inside the shadow world would swear that their universe just deformed, though in truth, the cause was a change in a higher dimension they could not sense. The same kind of misinterpretation may happen when we look at the constants of nature. The parameters we can measure could be mere projections of deeper structures, and what appears as an unlikely balance might simply be the shadow of symmetry in a space we cannot see. In plain terms, the universe we observe might not be the full object, but the footprint of a larger geometric entity, flattened by our limited access to its dimensions. This idea is not a poetic flourish. It has a foothold in serious theories. High-energy physics already invokes extra dimensions to unify forces and particles. In those models, the constants we measure are not fundamental. They are residues of how extra dimensions are folded or compactified to beings like us, confined to three extended dimensions. Those folds look like arbitrary numbers, but from the higher perspective, they could be as natural as the curvature of a sphere. If that is true, the apparent fine-tuning of our universe might not be fine-tuning at all. It could be an illusion born from the act of projection. The true configuration may be broad and stable, but when compressed into our three-dimensional understanding, it appears as a narrow ridge between extremes. What we call a knife edge could simply be the cross-section of a wide plateau. The concept carries a warning. Whenever we try to reason about probabilities in a multidimensional landscape, we risk confusing what is common in one projection with what is rare in another. A population that looks sparse when viewed from above may appear dense from the side. So when we say our universe occupies a special or unlikely position, we may be reading a distorted shadow of a broader reality. Imagine a sheet of paper representing our visible physics, laid across a room filled with invisible structures. Every constant we know is a coordinate on that sheet, but each depends on unseen factors floating through the rest of the room. If the sheet happens to intersect a higher dimensional pattern, the points of intersection will trace a shape that looks deliberate, but the pattern's origin lies elsewhere, in the full space. What looks like design from within the sheet is simply geometry from outside it. This perspective reshapes how we interpret coincidence. The proton and neutron masses might be tightly correlated, not because they were adjusted to match, but because both descend from a single relation in a higher dimensional framework. Their difference, the one that determines the existence of stable matter, might be locked by geometry rather than tuned by chance. The same logic can extend to the forces of nature. What we call electromagnetic strength or gravitational coupling could emerge from the curvature and topology of the extra dimensions. Why it matters is that projection turns the philosophical question of fine-tuning into an empirical one. If constants are shadows of higher dimensional shapes, we can, in principle, look for signatures of those shapes, subtle deviations in particle properties, patterns in cosmic background radiation, or correlations in the masses of new particles could all reveal the higher structure. The more consistent those patterns become, the less room there is for the narrative of improbable coincidence. Still, this projection idea creates its own paradox. If the higher space explains the numbers, what explains the higher space itself? Do its own parameters need tuning? Or does the chain of explanation end there, at a geometry so stable that it allows every lower projection to exist within its bounds? We may never have direct access to that space, but we can glimpse its shadow in the data we collect. Much like the moving outline of the cube on the wall, at its core, the shadow argument is both humbling and liberating. It tells us that the patterns we see may not mark the edge of understanding, but a hint of deeper order. Yet it also reminds us that our intuition for probability and balance is unreliable when stretched beyond the senses evolution gave us. What seems miraculous might be ordinary in a dimension we cannot yet imagine. Somewhere between the geometry of possibility and the physics we can measure, there must be a bridge linking projection to perception. The next question is whether our methods of counting and comparing can survive that bridge, or whether they collapse under the weight of infinity itself. In a universe vast enough to contain every combination of matter and light, it is not obvious how to count. You might think that counting universes is like counting stars or galaxies. But when the number approaches infinity, the idea of a total breaks down. Physicists call this the measure problem, but it is also a problem of perspective. What do you count as one? And who gets to do the counting? Imagine a survey of worlds. You list every region where stars form, where chemistry endures long enough for life to evolve, and where observers may arise to ask questions. If the cosmos is infinite, that list is endless. To make sense of it, you might decide to weigh each universe by the number of observers it produces. But this choice immediately changes the picture. Universes that spawn more observers gain more weight in your statistics. Those that produce only a few, even if they last longer or shine brighter, become almost invisible. The census of observers replaces the census of worlds. This may sound fair, yet it introduces a quiet bias. If we give every observer equal weight, then regions where conditions allow vast populations dominate the count. Even if such regions are rare in total volume, They become typical in the sense that most observers live there. Under that logic, the universe we inhabit should be one of those crowded ones, dense with civilizations. The sky should shimmer with artificial signals, yet we look and hear only silence. The contradiction is familiar, wrapped in the name of Fermi's question, where is everybody? In plain terms, when we try to count observers rather than universes, the results seem to predict far more company than we actually see. To reconcile this, some suggest that the measure should not count individuals but civilizations, or entire biospheres. Others argue for weighting by total entropy produced, or by energy converted into complexity. Each choice leads to a different notion of what is typical. None of them are self-evident. The act of counting becomes an act of definition, and the definition shapes the conclusion. Consider a simpler analogy. In a city, you can take a census by households or by residents. If every household has roughly the same size, the results agree. But if one building contains thousands of people and another only a few, counting by household versus counting by individual gives wildly different pictures of the same city. The same holds for the cosmos. If some universes host dense clusters of observers, while others host only a handful, our view of what is normal depends entirely on the counting method we choose. The situation grows stranger when infinities appear. If the multiverse truly contains an infinite number of regions, then there are infinitely many observers in every possible condition. Without a way to regulate that infinity, probabilities lose meaning. Any outcome that can happen happens infinitely many times. Under those rules, saying one outcome is more likely than another becomes impossible. To salvage the idea of prediction, cosmologists must invent artificial cutoffs, defining finite boxes within the infinite and taking limits. But those limits depend on how you slice the infinity, and different slicings yield different answers. This uncertainty does more than frustrate theorists. It challenges the idea that probability itself has objective meaning at the cosmic scale. If we cannot define what typical means among infinite possibilities, then fine-tuning arguments, anthropic reasoning, even the notion of a likely universe, all stand on shaky ground. We may still speak in terms of likelihood, but the numbers behind our words dissolve into ambiguity. Why it matters is simple yet profound. Without a clear way to count observers, we cannot tell whether our existence is rare, common, or inevitable. We can only note that we exist, that the constants allow it, and that no clear measure tells us how unusual that fact is. It may be that every possible observer feels equally special because each can only see from within one realization. In that sense, the feeling of uniqueness is built into the act of observation itself. There is, however, one empirical thread to hold. We can test what we do see. We can look for signals of other civilizations, for deviations in cosmic background radiation that suggest regions of differing physics, for anomalies in particle behavior that hint at a larger ensemble of worlds. So far, every search has come back empty. The silence does not prove we are alone. It only shows that whatever ensemble exists beyond us, it does not leave an obvious mark on our sky. Think of this silence as data. If vast multiverses teeming with observers were common, we might expect to detect at least faint traces of them. The absence of such traces suggests that the conditions producing observers like us are not just narrow, but sparsely distributed. Perhaps we are not at the typical edge of a crowded shoreline, but in one of its loneliest coves. That does not mean we are central or chosen. It simply means the geometry of existence may favor emptiness over company. At its core, the census of observers forces us to confront the limits of our reasoning. We may never build a catalog of all possible minds, nor find a consistent measure for comparing infinities. But by acknowledging that limit, we also recognize a deeper lesson. The act of counting can shape the reality we think we describe. Our definitions create the boundaries within which our logic operates. When those definitions fail, what remains is humility. The next step in our story is to ask what humility implies. If every method of counting breaks, and every projection reveals a different center, what are we left with besides awe? To answer that, we must leave the mathematics and step into the echo it leaves in our understanding of existence itself. A night sky is never truly silent. Even in the emptiest places, starlight hums against the eye, a faint vibration of meaning in the dark. We have mapped galaxies, weighed atoms, and modeled the first seconds of time. Yet we stand unsure whether any of it had to be this way. Every calculation points to fragility. Every attempt at counting collapses into uncertainty. Still, there is something in that fragility that speaks to us, as if the universe were not built for comfort but for reflection. The story of fine-tuning began as a mathematical puzzle. It ends as a meditation on perception. What does it mean for a universe to be balanced on a knife edge, when the very notion of an edge depends on the way we choose to measure? Perhaps the constants are not chosen at all. Perhaps they are the way geometry allows existence to appear, like a pattern carved by necessity rather than by intention. If that is true, then the universe is not a product designed for life, but a context in which life is one of the rare forms that can read the pattern. The narrowness of our situation becomes part of its beauty. We live in the slender gap where chaos and silence cancel, a space wide enough for thought to form and question itself. In plain terms, our fragility is not a flaw, but a signature. It tells us we are part of a structure that permits awareness only in the thinnest layers, like frost forming on the edge of night. The older we become as a species, the more we are forced to see that our ideas of safety, centrality, and design belong to our survival instinct, not to the architecture of the cosmos. The universe is not kind or cruel. It is indifferent. Yet in that indifference, we find a strange companionship, for it is precisely because the universe does not bend to us that our consciousness can discover its scale. The notion that we might be misreading shadows from higher dimensions does not make us insignificant. It makes us participants in a larger geometry that includes the act of observing itself. Every question we ask is part of the projection. Every experiment, every telescope, every simulation adjusts the light, changing the shadow we see. In learning, we do not escape the illusion, but we refine its contours. Why it matters is that knowledge and humility grow from the same root. The constants are not clues to a secret author, but reminders that meaning is something we project into the vast indifference of physics. We are the voice that the universe gained by accident, and now that voice wonders aloud why there is sound at all. In the long view, the measure problem becomes more than a technical puzzle. It becomes an allegory for every act of human understanding. We choose what to count, and the act of counting changes what we see. We define typicality, and in doing so, we define ourselves. There may never be an ultimate measure that tells us whether our place is ordinary or extraordinary, but the pursuit of that measure, the endless recalibration of our thinking, is itself what makes consciousness more than a biological process. The philosopher in the observatory and the physicist in the lab are chasing the same faint light. They both look for structure within uncertainty, pattern within noise. The result is not certainty, but perspective. As we realize that edges and centers depend on the maps we draw, we also realize that maps are all we have. Near the end of every long night of observation, when instruments cool and screens dim, there is a quiet recognition that nothing we find will make the cosmos care more or less about us. Yet we look anyway, because looking is our way of existing. We are the boundary, the place where the inanimate begins to ask what it is doing here. Perhaps this is the final echo of the fine-tuning paradox. The universe is barely habitable not because it was built that way, but because awareness itself is a boundary phenomenon. It appears only where the conditions are almost too precise to last. That may be the true symmetry hiding behind all the numbers the mind as the fleeting equilibrium of matter learning to see itself. And when the stars fade and the last observer asks what it all meant, the answer will not come from outside. It will rise quietly from within the question, as it always has. If the universe is a projection, then what unseen shape is casting us into being? And will that light ever turn so we can see the source?